So we are very happy today to have Bill Fischer, who is a PhD candidate at Simon Fraser University, British Columbia. His current research focuses on utilizing tourmaline as a vectoring tool in mineral exploration. Specifically, his research is about identifying spectral, chemical, and isotopic variations of tourmaline in hydrothermal systems. His research interests also related to physical description and formation of ore-bearing breccias. He received a master's degree in 2014 from the University of Nevada, Las Vegas, and a BSc 2012 from St. Norbert College in Wisconsin. In addition, he's an industry person and he's a project geologist for Imperial Metals Corporation since 2014. The platform is yours, Bill. Please take it away.
All right. Well, thank you for that lovely introduction. And greetings, everyone, and thank you again for attending today. Today for this talk, what I wanted to share with you is some of my findings from my doctoral research on hydrothermal tourmaline at the giant copper porphyry system located in southern British Columbia, Canada. And specifically, what I want to share with you today is some of the chemical and spectral data that I've collected from tourmaline in and around the mineralized AN tourmaline breccia pipe that occurs in the solar system. So for those who were not aware, tourmaline is a fascinating mineral that can be applied to a variety of geologic investigations. And that's because it can occur in a wide range of geologic settings. It has a large stability field, negligible diffusion rate, diverse chemical variations consisting of 37 known subspecies. It's an excellent reservoir for boron isotopes. And as far as economic geologists are concerned, it can occur in all major ore deposit types. Now, when I was first starting to look into tourmaline as a research topic, two characteristics really stood out to me in my preliminary readings. And those two characteristics were the diverse chemical variations that we see in tourmaline, as well as its occurrence in ore systems. So that really made me start asking the question, can tourmaline chemistry perhaps indicate ore mineralization? And what I mean by that specifically is there a certain subspecies of tourmaline that is commonly more associated with ore mineralization in any given ore system, while other subspecies are not? Or can we monitor subtle variations in a tourmaline's chemistry and see if that correlates with increases in ore mineralization? Now, unfortunately, the collection of tourmaline data with respect to the mineral exploration industry has its shortcomings. First, quantifying tourmaline's chemistry requires sophisticated analytical instruments. Instruments like scanning electron microscopes, microprobe, laser ablation ICP-MS. If not one, all of these instruments are being used to quantify tourmaline's chemistry, and these instruments require highly specialized third-party experts to operate. In addition to that, the collection of the data using these instruments can be a significant time investment, as well as the rigorous petrographic analysis that needs to be done on tourmaline and the ore system that it occurs in, so you actually understand what that chemical data that you're collecting from tourmaline is actually telling you. Today in my talk, we're going to be looking at some tourmalines with a significant variation in chemistry when it comes to growth zones within an individual tourmaline grain. And if you don't know what those individual growth zones are telling you with relationship to geologic events at an ore system, well then that information that you're gathering chemically from tourmaline isn't going to tell you much. And when you add all three of these points up, none of them are very cost effective. And when it comes to mineral exploration, when it comes to the industry, if it's not cost effective and if it's not time efficient, then the technique's not going to be used. So we really need to, if tourmaline chemistry is going to be efficient in mineral exploration, then we need to find a more cost effective and time efficient method to monitor these variations. So that's where I thought, maybe reflectance spectroscopy could help us out. So for those who aren't familiar with what reflectance spectroscopy is, it's essentially the real-time identification of minerals via spectral measurements that are collected when emitting minerals with visual, near, and shortwave infrared light. And what's ideal about reflectance spectroscopy is it can identify minerals that are very difficult to identify in hand samples, such as variations in white micas, phyllosilicates, and also other minerals in solid solution, tourmaline being an excellent candidate for that. Now, over the past 3 decades, reflectance spectroscopy has gained significant traction in mineral exploration due to its easy capability for data replication. It's extremely easy to train new users on. Simply teaching people how to point and click a spectrometer in some cases, you're already starting to collect data. And compared to more quantified, sophisticated instruments, it's much more cost-effective for mineral exploration. So the question here is quite simple. Can we monitor tourmaline chemistry variations spectrally? And so for the spectral data that I'm going to be presenting to you today on tourmaline was collected from the 2 spectrometers we see here. In situ data was collected from the TerraSpec Halo Mineral Identifier gun. And we also were able to collect regional spectral data over the AM tourmaline breccia pipe using a spectrometer attached to a drone courtesy of Echo Labs located here in British Columbia. So before we get into that chemical and spectral data, a brief introduction is necessary for the giant copper porphyry system as well as the AM tourmaline breccia pipe. So for those who aren't familiar, the giant copper porphyry system is located in Western Canada along the US-Canadian border in British Columbia, roughly 150 kilometers east of the city of Vancouver. Now, a uranium-lead zircon age date of the Inverme stock, a granodiorite to dioritic intrusion responsible for mineralization in this porphyry system, returned an age date of 24.1 million years, which puts it in the middle of the ancestral Cascadia orogeny and formation of the ancestral Cascadia arc from 29 to 22 MA. So this is actually a very young age of mineralization for porphyry systems in British Columbia. So when you're comparing it to systems in the Intermontane or in the Golden Triangle, it doesn't really seem to make a lot of correlation. But when you start looking to porphyry systems in the ancestral Cascadia orogeny to the south, in Washington as well as Northern Oregon, a lot of similarities start to arise. These porphyry systems also see tourmaline alteration spatially associated with copper mineralization. And in addition to that, tourmaline breccia pipes that are copper enriched can also occur directly associated with these porphyry systems. So now that we've introduced its larger regional scale, let's take a look at the giant copper property itself. So the giant copper property consists of 8 mineralized zones. 7 of these zones are tourmaline breccia pipes, and 1 zone consists of conventional porphyry style mineralization. Now, of these 8 mineralized zones, the AM breccia located here is the most thoroughly explored of these systems with an inferred resource of 30.2 million tons and a cutoff grade of 0.72% copper. And for those who are familiar with tourmaline breccia pipes, the AM breccia shares a lot of similarities with tourmaline breccia pipe systems that we see globally. And that's pretty important because tourmaline breccia pipes, not only are these high-grade systems that can exceed to great depths, some exceeding greater than 1 kilometer into the crust, but due to their vertical structure, they're ideal targets for underground mining and perhaps subblock caves. So next, let's look at the AM breccia a little more in depth. This is the geologic map of the AM breccia at surface. And like all tourmaline breccia pipes, the AM breccia demonstrates concentric zonation with its breccia textures. It consists of an outer shingle breccia, shown here in darker red, and shingle breccias referring to the elongated, oriented clasts that appear like shingles on a roof, hence the name shingle breccias. Now, it's this orientation of clasts that is very important because it streamlines fluid flow within the outer margins of the breccia pipe, promoting copper sulfide mineralization. And this is why within tourmaline breccia pipes and at the AM breccia, we see our significant and most consistent ore grades on the outer rim, anywhere between 0.7% to 16% copper with significant silver along with our high copper grades. Now, within this shingle breccia outer zone, fluid flow can be so significant that instead of seeing mineralized breccias, as we see here, we'll simply end up with massive sulfide precipitation. As you can see, we can have significant copper within those samples. And of course, in situations where we don't get copper sulfide mineralization, they are rare, we will simply see tourmaline cement holding together our shingle breccias. Now, as we move to the center of the pipe, we start seeing the more conventional fragmental breccia, where we see lower, more sporadic copper grades, and that's due to the more chaotic nature of the breccia in this area of the pipe, clasts are more random in their shape and orientation and their size, and this demotes fluid flow, thus leading to more sporadic ore mineralization and promotes precipitation of gangue minerals such as tourmaline and chlorite. And as I mentioned, grades can be sporadic. So you can see here from these four samples of fragmental breccia, we have very low grade, some moderate grades, but we can also see some very high grades within the center of the pipe. So now that we've seen the AM breccia at surface, let's take a look at what it looks like in the subsurface by looking at two cross sections, A to A prime, which focuses on the north nose of the AM breccia, where the vast majority of the exploration drilling has taken place. And then we'll look at a cross section B to B prime, which gives you a better understanding of the true width of this tourmaline breccia pipe. So the AM breccia has been delineated quite nicely for approximately 400 meters into the subsurface. Deep drilling in 2006 and 2007 beneath the AM breccia was able to extend the breccia pipe for an additional 400 meters, totaling 800 meters now, and is still open to depth. In fact, when we look at the breccia at this 800 meter depth, we can see that we're still in good fragmental breccia textures with pretty significant copper grades. As we look at the geology, we see our shingle breccia encompassing our fragmental breccia in the center. And when we look at our numeric model, we can see copper with red showing greater than 1% copper, correlating very nicely to our shingle breccia textures. And in the center where we see our fragmental breccias, we're seeing more sporadic, lower grade copper. In addition to seeing breccias with good mineralization at depth, we're also starting to see biotite alteration. So this is actually very key in tourmaline breccia pipes, because with exceeding depth, we actually start seeing a variation in alteration, where instead of seeing tourmaline as the dominant ore mineral, biotite begins to take over as we enter a deep potassic zone. And within this deep potassic zone, there is a potential for copper enrichment, where bornite along with chalcopyrite begins to occur. So next, let's look at B to B prime. Also in 2006 in the 2007 drilling program, the southern rim of the AM breccia was confirmed. And as you can see, we drilled essentially right into shingle breccia that is quite high grade. Also, you can notice that there's a significant amount of infill drilling that needs to take place, as well as delineating this high grade outer margin at depth. Now, as I mentioned previously, the AM breccia shares a lot of similarities with tourmaline breccia pipes on a global scale. And what I like to do at this part of the talk is give a one-to-one comparison to probably what's the most world-renowned tourmaline breccia pipe, and that's the Fischer breccia at the Rio Blanco Los Bronces porphyry system in central Chile. So these cross sections, the B to B prime for the AM and the Fischer, are set to near identical scales. And so essentially at the AM, we've identified the first 400 meters of potential significant tourmaline breccia pipe. We know it continues for another 400 meters for a total of 800. And we have evidence of potentially intersecting a deeper potassic copper enriched zone at depth. And what is also a very fascinating upside for exploration at this property is the mineralization still remains open to depth, and a lot of different areas can still be drilled to identify that high-grade shingle rim. So now that we've seen the AM at the surface and subsurface, wanted to put it together in a nice little video that I've rendered in Leapfrog. And if this video doesn't play well for you, you can find the link in the chat box in Zoom. So as I begin the video, we're going to rotate from the surface mapping of the AM breccia and go into the subsurface, where we see the underground and surface drilling that has been done at the AM breccia. And now our geologic polygons are turning on. Our dark red again is our shingle breccias, our brighter red is our fragmental breccias. And note how that shingle breccia just conforms very nicely to that inner fragmental breccia. And you'll notice as this model rotates that there's a lot of area that of infill drilling that can be done to further discover new zones of that high-grade shingle breccia. Now, as we shift from a geologic to numeric model showing copper grade, copper, warm colors indicating high copper, we're essentially averaging a greater than 1% copper in this north rim of the AM breccia. And of course, the southern rim is less identified, but you can see there's a significant amount of low-hanging fruit that can be drilled off, as well as a high probability of intercepting this high-grade shingle breccia at depth. So now that we have a good introduction and understanding of the AM breccia, let's get back to talking about tourmaline. So tourmaline in and around the AM breccia can occur in host rocks and breccias. In the host rock, the ladner siltstone, tourmaline can occur in vertical sheeted fractures, such as these, which is also a common characteristic on the margins of tourmaline breccia pipes, and can occur disseminated within the host ladner siltstone, or as prismatic crystals, or in microfractures within that siltstone. Now in the breccia, tourmaline can occur both in the matrix and class. It can occur bladed, prismatic, and in the matrix, it occurs as a mineral cement holding the class together. And in the class, it occurs disseminated. And as you note, the tourmaline has a strong spatial association with our primary ore mineral at the AM breccia, chalcopyrite. Now, when we look at the micron scale of these tourmalines, we start seeing some very fascinating textures and growth zoning. We see variable pleochroism in our tourmaline at the AM breccia. All tourmaline at the AM breccia at the micron scale will always consist of two main growth zones. The first being an inner brown growth zone, as we see here, and that inner brown zone will typically always be rimmed by an outer blue zone, exhibiting this somewhat of a bearded texture. We also see subordinate innermost ochre zones that always occur inside brown zones, and subordinate green zones that are sandwiched between brown and blue. Another very interesting observation that we made with tourmaline, specifically tourmaline occurring outside distal from the AM breccia, we see that our brown tourmaline growth zones do not have an outer blue rim. So very interesting observation to note. And before we get into looking at the chemistry of these different growth zones in tourmaline, it's important to note that all tourmaline that was analyzed is interpreted to be hydrothermal tourmaline. So for today's talk, I'm primarily going to be focusing on the brown and blue zones when it comes to the chemistry. I have the ochre and green zones plotted on the ternary and scatter plots following, but I'm primarily just going to be talking about blue and brown zones since those are the most dominant. Ochre and green, again, are subordinate and not always occurring in tourmaline in and around the AM breccia. So blue zones, regardless of their association inside or outside the pipe, are typically alkali-rich, shorelitic to dravitic in composition, with high concentrations of iron, arsenic, and tin, and low concentrations of fluorine, titanium, vanadium, and chromium. Our inner brown zones, on the other hand, are calcic-rich, with minor excursions into the alkali group, and are typically ferruvitic to uvitic in composition, with high concentrations of fluorine, titanium, vanadium, and chromium. Now, it's this high concentration of titanium with respect to the blue zones that is likely what's causing this brown pleochroism within our inner brown growth zones in tourmaline. And that titanium solubility is likely being driven by higher concentrations of fluorine within the hydrothermal system. And that also makes sense as to why we see outer blue zones. Blue zones, typical blue pleochroism in tourmaline typically refers to low titanium and high iron. And this also confirms this idea based on the low fluorine that we see in our outer blue growth zones. Another very interesting thing that we see in the tourmaline chemistry in and around the AM breccia is it seems to be a function of where tourmaline is occurring with respect to the AM breccia pipe itself. And what I mean by that is, regardless of if you're in a blue and or brown zone, if you're in a tourmaline if you're looking at a tourmaline's chemistry inside the AM breccia pipe, it is typically iron rich. When you're looking at tourmaline inside the pipe, when you're in a blue zone, you're typically seeing shorelitic tourmaline, while brown zones in tourmaline inside the pipe are ferruvitic tourmalines. So these are both iron-rich variants, shorelitic being alkali iron end member, ferruvitic being calcic iron end member. Now, when we look at tourmaline distal to or outside of the AM breccia pipe, we see a dramatic shift in chemistry. Instead of seeing iron-rich tourmalines that we see inside the pipe, outside the pipe, we see our blue and brown zones are more magnesium-rich. Our blue zones occurring outside the pipe are dravitic, the magnesium alkali end member, while brown zones are uvitic, the magnesium calcic end member. So when we look at iron and magnesium in this scatter plot below, we can clearly see that tourmaline chemistry does correlate well with mineralization at the AM breccia. It seems that when we have tourmaline that is occurring with ore or ore-bearing textures, we're seeing an iron enrichment. While on the other hand, when we're looking at tourmaline away from copper mineralization and occurring in rocks not containing ore-bearing textures, they are more magnesium rich. So to answer that first question that I introduced this talk with, can tourmaline chemistry help us perhaps vector or identify variations in an ore system? It seems the answer can potentially be yes. At least at the AM breccia, it seems that we can differentiate between mineralized and barren rock based on this play between iron and magnesium. Now the real question is can we identify that spectrally? But before we get into the spectral data, I want to also show this tourmaline chemistry in a spatial relationship within the AM breccia pipe. So here we're looking at a cross-section, A to A prime, showing tourmaline occurrences, and this is probe data. In cross-section A, we're looking at weight percent in iron of tourmaline, as well as copper percent based on the size of the circles. And in cross-section B, we're looking at magnesium weight percent. So going to cross-section A, tourmaline inside the pipe, whether it's occurring at the surface, at the 400-meter mark, or at significant depth, tourmaline inside the pipe will be iron enriched, while tourmaline outside the pipe is iron poor. And as we move closer to the AM breccia contact, that iron concentration increases. On the other hand, when we look at magnesium concentrations, tourmaline on the outside of the pipe is magnesium rich, greater than 4 weight percent magnesium, while tourmaline inside the pipe is significantly less magnesium than tourmalines occurring outside. So let's see if we can identify these chemical variations that we see in tourmaline spectrally. Now, very little research has been done on spectral properties of tourmaline, and if we were all to take a break and start doing a literature search for spectral reflectance data on tourmaline, we'd all eventually come to a study by Phil Beerworth in 2006, who characterized the spectra of 3 end-member tourmaline species: elbaite, shown here in black, dravite in blue, and schorl, the iron-rich end-member, shown in red. So we know that we have magnesium-rich tourmaline and iron-rich tourmaline at the AM breccia. So the idea is do those spectra from those tourmaline reflect these end-member spectra? So for end-member dravite, we will typically see iron hydroxyl features lower than 2250 nanometers, with magnesium hydroxyl features at 2353 nanometers. End-member schorl, on the other hand, will have an iron hydroxyl feature greater than 2250 and a magnesium hydroxyl feature at 2369. So the hypothesis is quite simple. Our magnesium-rich tourmaline at the AM breccia should reflect the end-member magnesium-rich dravite spectra. So I was anticipating, prior to collecting the spectral data, that we should see iron absorption features less than 2250 and magnesium absorptions less than 2361. Now, 2361 may seem a bit arbitrary, but it's essentially just the median between the 2353 and 2369 magnesium absorption features for end-member dravite and schorl respectively. And for schorlitic tourmaline or iron-rich tourmaline at the AM breccia, we would expect that to reflect end-member schorl spectra with iron absorption features greater than 2250 and magnesium absorption features greater than 2361. So let's take a look at some of the spectra from the AM breccia and see if these hypotheses hold up. So here we have the end members off shaded. So first we're going to look at a spectra from tourmaline outside the AM breccia pipe. And as we can see, it correlates very nicely, sharing a lot of similarities to the end-member spectra of dravite. We see an iron absorption feature less than 2250 and a magnesium absorption feature less than 2361. Now, all tourmaline outside the AM breccia will exhibit a magnesium absorption feature less than 2361 and an iron absorption feature less than 2253. My hypothesis was off by 3 nanometers. I'll live. Tourmaline inside the pipe, that is iron rich. Well, let's take a look at that spectra now. will reflect the end-member spectra of Shoro, where we see an iron absorption feature greater than 2253 and or a magnesium absorption feature greater than 2361. Now, this spectra in magenta clearly shows both an iron absorption feature and a magnesium absorption feature greater than these benchmarks listed in in my hypotheses, but that isn't always the case. And what's more common to see in spectra of tourmaline inside the AM breccia is an iron absorption feature that's greater than 2253 and or a magnesium absorption feature greater than 2361. So for example, if it has an iron absorption feature greater than 2253, then it's most likely not going to have a magnesium absorption feature greater than 2361 and vice versa. So it seems that the hypothesis is holding up for 3 spectra from tourmaline at giant copper at the AM breccia. So let's take a look at the remaining 584 spectra points. So here's a scatter plot showing 587 spectra from tourmaline in and around the AM breccia pipe, showing magnesium hydroxyl features on our y-axis and iron hydroxyl features on our x-axis. And as you can see, we have very distinct grouping between tourmaline occurring outside the breccia pipe in blue and tourmaline inside the breccia pipe at red. Again, tourmaline outside the pipe is showing a magnesium absorption feature always below 2361 and an iron absorption feature less than 2253. Tourmaline inside the pipe shows an iron absorption feature greater than 2253 and or a magnesium absorption feature greater than 2361. So unfortunately, I don't think we can at this time identify exactly this subspecies of tourmaline from spectral reflectance data, since we're dealing with both calcic and alkali tourmalines at the AM breccia. It's a question as to what calcium at the X side in tourmaline might do to the spectra to change it. But it seems that even though we have calcic tourmaline, it's still conforming to an end-member magnesium-rich spectra. So it seems that we can differentiate between this magnesium and iron exchange that's occurring at tourmaline in and around the AM breccia at the Y site. So I would say that spectral reflectance data from this work can monitor variations in tourmaline chemistry that have been quantified. So let's take a look at these patterns at the surface. So here we're looking at a planar map of the AM breccia. Its contact shown by the dotted line. North is to the right. And I've also included on this map the barren camp breccia. As you can see, it's barren of copper, but still has tourmaline, hydrothermal tourmaline alteration associated in the pipe. Here we're looking at copper concentrations. As we would expect, copper concentrations are high in the AM breccia, low outside of it. When we look at magnesium hydroxyl features, we can note that tourmaline inside the pipe will have a magnesium hydroxyl feature greater than 2361. And when it doesn't, those tourmaline will have an iron absorption feature greater than 2253. So what's interesting to note about these 3 figures is that it notes that the camp breccia, which is a tourmaline breccia pipe as far as we're concerned, that unfortunately is copper barren, but it is showing the tourmaline characteristics of rock that is devoid of mineralization. So it also seems that we can identify potentially mineralized from barren tourmaline breccia pipes in the giant copper porphyry system. So next we're going to look at A prime cross sections, those same cross sections that we looked at probe data for tourmaline, but now we can see the significant amount of data that we have to work with spectrally than we do with probe data from tourmaline. Whether we're at the surface, midway through the pipe, or at its greatest depths, we can see that the spectral characteristics of tourmaline in and around the giant copper property correlate to these rules that I've established in the previous slides. Inside the pipe, iron hydroxyl features greater than 2253. And when they aren't, we see magnesium absorption features greater than 2361. So next I want to shift gears and start talking about regional spectral data that we've collected above and around the AM breccia. And this was again done in partnership with Echo Labs, the company that specializes in hyperspectral remote sensing using drones. And the idea that I had and what I wanted to try to accomplish with this part of the research was If we can identify tourmaline spectrally at a regional or deposit scale, then perhaps we can expedite mineral exploration in ore districts that are known to have a strong spatial association between tourmaline and ore mineralization, such as the ancestral Cascadia Porphyry district, or the much more well-known and significantly larger Porphyry belt, Andean Porphyry belt in central Chile, an area that would be very useful for, very applicable for reflectance spectroscopy. So our airborne spectral surveys, we did over 30 flights with the spectrometer attached to a drone at a 10-centimeter ground sampling distance, collecting we created spectral correlation mapping using RGB false mineral maps, and we're able to confirm those using our wavelength mapping aluminum, magnesium, and iron hydroxyl features. We were also able to apply in situ data to these surveys that we collected from tourmaline in and around the pipe, and we're successfully able to identify tourmaline at a regional scale. So let's take a look at some of this data. Here's the AM breccia, the white line representing the contact of the breccia pipe. This is our high-res image collected from this survey. Next, we're going to look at our RGB false color spectral map, which identified our three dominant minerals at the AM breccia, tourmaline, chlorite, and white mica, and assigns them colors. Tourmaline and white mica were both given red and blue respectively. And as we can see inside the confines of the AM breccia, a significant magenta signature, which stands for a high concentration of both tourmaline and white mica, with lesser chlorite in the pipe. Outside the pipe, we see chlorite is dominant with lesser tourmaline and white mica. So it seems that we're identifying significant abundances of tourmaline inside the pipe that are linked to mineralization. But the question is, okay, are we actually truly identifying tourmaline spectrally, or are we perhaps identifying white mica that is masking as tourmaline? So to answer this, we're going to look at the three different wavelength maps for aluminum, iron, and magnesium hydroxyl features. First, we're going to look at aluminum hydroxyl. So inside the AM breccia, we have an aluminum hydroxyl feature that ranges anywhere between 2200 nanometers to 2215, showing off that nice green and yellow color. Outside the pipe, we see values that exceed greater than 2240, and that correlates very nicely with our high chlorite concentration. Chlorite doesn't have an aluminum absorption feature, so it's likely that we're picking up its iron absorption feature that occurs anywhere around 2250 nanometers. Now, tourmaline and white mica both contain aluminum hydroxyl absorption features at and around 2200, as you can see from the USGS spectral library data on white mica and sericite. It's also confirming an aluminum absorption feature at 2200. So it's likely that it could be suggested that we're identifying both white mica and tourmaline here. So one or the other could be masking. So at least at this stage, we have no information that suggests that we're not identifying tourmaline. But anything, the aluminum hydroxyl map is confirming the presence, at least of both tourmaline and white mica. Next, when we move on to iron hydroxyl absorption features, which white mica doesn't have one, we can see that we have iron hydroxyl features inside the pipe greater than 2270 to 2290. Now, this is key because since white mica doesn't have an iron absorption feature, but tourmaline does, whatever is occurring inside the pipe associated with this tourmaline and white mica concentration must have an iron absorption feature. So it could potentially be chlorite, but it also very well could be iron. It could also be our tourmaline subspecies, which we know inside the pipe can have the potential of having an iron hydroxyl feature greater than 2253 nanometers. So whatever minerals are occurring inside the pipe contain both an aluminum and iron hydroxyl features, which is again confirming correctly the presence of tourmaline. So lastly, we're going to look at magnesium hydroxyl features. So typically tourmaline will have a magnesium hydroxyl feature greater than 2350, as we see from its subspecies variants from Phil Beerworth's work. They occur in this area between 2353 and 2390, while white mica and chlorite typically will have a magnesium absorption feature less than 2350, and will have this later absorption feature at 2420 for white mica and 2440, 2450 for chlorite. So when we look at our magnesium absorption map of the AM breccia, we're seeing a significant magnesium absorption feature between 2340 and upwards to 2370 with those dark red areas. Now, unfortunately, those dark red areas could very well be this white mica, later white mica or chloride absorption feature. So with the help of Echo Labs, we wanted to take a look at the area where we expect to see that tourmaline magnesium absorption feature and what we refer to as TMG or tourmaline magnesium absorption feature. So next, what we did was we focused primarily in this wavelength zone. And what we're trying to target is this magnesium absorption feature that occurs anywhere between 2353 and 2390. If we're seeing a feature in that realm, we're pretty certain that it's tourmaline since white mica and chloride don't have that feature there. So when we look at this TMG map, we're seeing these yellow, green, blue pixels within the red area. And so those variations are lining up to a signature between 2375 and 2390. So that correlates very nicely with what we expect to see from the spectra of tourmaline at this wavelength range. And then all the deep red that is expressing absorption features greater than 2400 is likely that later stage white mica or chloride feature that we see. So the presence of all three of these features that correlates so well with tourmaline spectra seems to reaffirm that tourmaline identification was successful, and that by being able to identify tourmaline at a regional or deposit scale has the potential to expedite early phases of exploration and better prioritize areas in a land package in ore districts that have that strong spatial association between tourmaline and ore mineralization. So let's just wrap up this talk. Tourmaline occurring outside the AM breccia, more magnesium rich, has that dravidic to euvitic chemistry. Tourmaline associated with ore and ore bearing textures within the AM breccia are schorlitic to ferruvitic, iron rich. Tourmaline, therefore, chemistry can potentially differentiate barren and mineralized zones as well as pipes at the property. But again, I put potentially and site specific in there because tourmaline is a very erratic mineral when it comes to chemistry. So what we see at the AM breccia and giant copper might not apply to every ore system where tourmaline shares an association with copper. Lastly, it seems that spectral reflectance data can identify these variations in tourmaline, and identifying it at the regional scale has the potential to expedite early stages of mineral exploration. Once again, it's a pleasure to give this talk to all of you today. Thanks for stopping by and learning about the chemistry and spectral data of tourmaline in and around the AM breccia. If you have any questions, now's the time to ask them. And if you gotta go, my email is here. Just feel free to drop me a line. Thank you very much.
Thank you, Bill. That was awesome. Finally, somebody said something meaningful.
Oh, thank you.
Microanalytical techniques not gonna work for industry. It's super expensive, time consuming. So this is pretty interesting. So here we have lots of people join us today. I would like to ask Dr. Marshall if he can join us to open up the discussion part.
Okay, well, Bill, I'll just iterate those comments. That's a very well put together talk. Thank you very much. And I guess we can get the discussion going here. I have limited screen real estate here, and as Azam pointed out, there's a few different ways to ask a question. If I don't see you in the chat window or your hand come up on my screen here and you feel I'm ignoring you, maybe just shout out your question or your comments and we'll get to it. So would anybody like to start the discussion?
I think we have a couple of questions right now. One is rather short, that was asked by Christian Dreibness, and how much SN is high SN? You mentioned this in the slide with the defining spectrum, standard spectrum. How much tin is high?
So yeah, tin content.
Oh, how much tin is high tin? Yes. That's a good question. I don't have the exact numbers off the top of my head. I haven't looked at that data in a few weeks, but I can get that data to you if you send me an email. When I'm saying, of course, high tin referring to with respect to those brown zones. This is something, let me just speak a little more about what this elevated tin means in these blue zones. Typically, regardless of if you're in a porphyry copper system or a tin tungsten reduced intrusion related system, if tourmaline is occurring in that ore system, hydrothermal tourmaline related to that ore depositional event typically has high tin. Something that we first set out to do with this project is identify copper within these blue zones that share such a strong association with, that show a lot of evidence for being related to copper deposition at the AM breccia. And although we didn't find any elevated copper or silver or lead or zinc, what we did find was tin, and that's something that seems to correlate in trace element data from tourmaline at these all these ore deposits. Sorry for not being able to give you an exact answer on the concentration of exact quantified values of tin. I can get that information to you if you would like to just get my email data and my email information and just shoot me an email with that question. I'll be happy to follow up with you later today.
Mm-hmm. But even with that, Bill, I think you can safely say it's pretty much trace amounts.
Oh yeah, it's not like yes, it's not nothing abnormally high.
We're not talking percentages.
Yeah, we're not talking percentages at all. No.
Bring them out.
And it's way lower than the amount of tin that we can get in white mine copper.
Right.
Okay.
So, Bill, there's also a question from Chris Beckett Brown there in the chat window. Can you see that?
Yeah. Host, what is the paragenic relationship between tourmaline and ore minerals, and how does it affect the subsequent tourmaline chemistry? Yeah, good question. So the paragenetic sequence, so as I mentioned previously, we have 4 main zones, growth zones within our tourmaline. Our innermost zone, which is a subordinate zone, is that ochre zone. So that's been interpreted based off of our boron isotopes that we've collected, as well as its geochemical signature, to most likely be this kind of hydrothermal magmatic earliest stage of tourmaline chemistry. It's not, we're not saying that it's fully magmatic, but it's most likely the growth zone that's containing the most inherited chemistry from the intrusion. It's the most titanium rich, it's the most fluorine rich of our growth zones. Our brown and blue zones, we're also interpreting to be more of a magmatic inherited chemistry, where our outer blue zones seem to be the most spatially and temporally associated with copper mineralization at the giant copper property. As well as the subordinate green. That subordinate green seems to be acting as the transition between our inner brown and outer blue. So that's something also that we see in tourmaline at the micron scale, tourmaline that shows a decrease in titanium, increase in iron will show that green pleochroism, and then when you lose significant titanium, it becomes that blue pleochroism. So it's likely that that blue growth zone is most closely temporally associated with the ore mineralization within these breccia pipes.
Okay, thank you. The next question is from Anar Valia. Would you mind to unmute yourself and ask your question? It looks not, so I can go through it. So it's from Azerbaijan. And the question is that, is it possible to observe tourmaline in low sulfidation systems?
Observe as in, does it occur in low sulfidation systems, or monitor chemical and spectral changes? Sure. If tourmaline is occurring, massive tourmaline with some chalcopyrite, yeah, I don't see why not. Tourmaline is a as you've probably heard referred to it in your geologic teachings as a garbage can mineral. And because of that, its chemistry can be very erratic. But within hydrothermal systems, we know that hydrothermal systems, the chemistry in these systems can change with space away from the center of them. So yeah, I don't see why not. We couldn't look at a study focused around tourmaline in a low sulfidation system. Could perhaps show similar findings to what was presented today. Also, as a precautionary tale, it also very well might not. There are studies that I've seen that potentially try to link tourmaline chemistry to ore mineralization with the idea of vectoring, but it doesn't always seem to be as readily apparent as it seems to be with the AM breccia. But I think what really helps with this tourmaline study is mineralization as well as ore-bearing textures are so, the contact is so sharp between, when you're in the breccia and when you're in the host rock. And that seems to have created a dynamic change that we can also see in the chemistry within those tourmalines.
Next question from Christian Driveness was that, did you try the spectral tourmaline mapping on a smaller scale, like hand specimen or thin section sized? And were you
that would be
able to verify your observations?
That would be, first of all, to answer your question, no, we have not tried that. I also didn't even think of that, but that would be quite interesting to do, because now I believe on the market, Malvern Analytical is starting to market this little pencil tip spectrometer where you can more precisely aim at these potentially specific areas within a grain of a mineral. So that would be something to look into. Thanks for that. Thanks for that idea. Something just to a question that I typically also get is, have you tried portable XRF? So we did try that, and it got extremely messy. Not messy in an actual mess, but it became very complicated to try to pinpoint the X-rays onto a single grain of tourmaline. We attempted it with the handheld and in the barbecue setup that it comes in, and we had to drill a piece of tempered glass at an angle of which the X-ray beams are coming out, and it just didn't work. And again, if it's going to take that much work to collect chemical data on tourmaline quickly, it's not going to be applied. And the great thing about this spectral data collection is you simply just take pieces of carbon tape, you block out the areas that you don't want to analyze, and that leaves you with tourmaline, so you're getting a tourmaline spectra. Pretty ideal that way. But great question.
Yeah, Bill, you actually have done, I mean, when you're using that tape, I mean, you are essentially doing it at a smaller scale at the hand specimen or thin section level. Yeah.
Yeah, true.
Yeah.
I
guess the question is if there is any use for tourmaline in gold mineralization.
Again, sure, could be. I think what's spectacular about tourmaline in ore systems, obviously it's probably not always occurring, but when it does occur, it definitely opens the door for you to do a lot of different analytical work to learn about how an ore system unraveled. And whether it be a porphyry or reduced intrusion gold system, reduced intrusion tin tungsten system, or perhaps a VMS or orogenic gold system. If you have tourmaline, you have all of these tools at your disposal. It's just a question of if they're going to work and be applicable to you.
Okay, the next question is from Ali. Would you like to unmute yourself and ask your question?
Hi, yes. Sorry, I joined late, so I don't know what was covered at the beginning. So I had this question, and I think sort of you answered that already about using portable XRF. And yeah, portable XRF, I use it a lot. And the minimum size that you can do is down to 3 millimeter, and that is maybe not enough for some samples. I was just going to suggest how about LIBS, like laser ablation, blast spectroscopy, like the new portable instrument, well, relatively newer portable instrument that is getting sort of foot in the mining business?
Right. Great question. Yeah, it's going to come down to really the ease of getting a spot size small enough to know that you're just analyzing the mineral of interest, in this case, tourmaline. So if with that new portable instrument, if it has the spot size capabilities to go that small, then yes, it very well could be. Also, keep in mind, something that I wanted to do with this research and was adamant about was using a portable reflectance spectrometer. So the TerraSpec Halo gun is made to be carried around essentially in a holster as you do geologic mapping, and you simply can just take it out. Every spectra collected from this Tourmaline study was collected in 20 seconds. So that's the kind of efficiency that the mineral industry is looking for. And that's why I gravitated towards that particular spectrometer for this study.
Thank you.
Yep.
So I have a question for you as well. If you put tourmaline away, what would be the next mineral that you would suggest to work on with this methodology?
Interesting. Just in general or at giant copper?
Something to go for a distal vectoring tool.
So just in general for any ore system, or
Porphyries typically.
or porphyries in general? Well, we're all familiar with observing variations in phyllosilicates and white mica. So obviously those are mineral groups that have been proven to be very efficient as vectors within porphyry systems. I would also be very intrigued to do more in-depth work with chlorite.
Okay.
So, something that, again, this isn't really news. It's been done with laser ablation ICP-MS at the trace level, looking at vectoring in green rocks towards center of porphyry systems and better orient yourself in mineral exploration. But chlorite, we have iron-rich chlorite, we have magnesium-rich chlorite. Perhaps there's variations spectrally that you can identify in chlorite around porphyry systems, in and around porphyry systems, that can be an efficient vector. Again, chlorite's a mineral that we see in low temperature alteration zones of many ore deposits, and is much more common. So that definitely could be a mineral of interest to look in for this type of study. The laser ablation data that's been done out of codes seems to be very, very well done, and seems to be show chloride as a very useful vector. But if you can take it to that next step and make it more cost effective and time efficient with reflectance spectroscopy, that would be a groundbreaking.
Yeah, that's true. Dan, would you like to ask something or add something?
Yeah, so there's a couple of things. One is epidote is another really good candidate, but really any of the alteration minerals that seem to change their chemistry with respect to ore grade. And I guess the thing here is that there's a lot of points on that diagram. Bill has done a really large pile of work here to get all this data together. And, if we want to move to tourmaline and gold deposits, that's certainly doable, but it's going to take another student or another big study like Bill has done here to try and sort out the tourmaline versus the ore grades in gold deposits, likewise in the epithermal deposits. It's all doable. I think Bill's opened a really, interesting door here into looking into this. And then just my last comment would be coming back to the XRF. I suspect that the manufacturers, if this gets picked up by exploration, especially on the SWIR side, I suspect the XRF manufacturers will try and come up with a better system of collimators and collection on the XRF units so we can get the sample size down. But you know, that's further down the road, but I suspect that will happen.
Okay, I guess here we're running out of time for our meeting, and I thank everyone for the attendance. Final reminder, if you need a certificate, the link is in the chat. And I guess see you in a couple of weeks, guys. Thank you for coming. And thank you, Bill, for incredible talk. That was really awesome.
Was a pleasure. Thank you for having me.